Continuing with our integration using substitution method, let's start with the integral of sine 3x cosine 3x dx. In this one, I just randomly picked sine 3x to be my substitution. You can use cosine 3x and it'll still work out as long as you do all your technique right. Letting u be sine of 3x, we have u equals sine 3x. Taking the derivative, we have du cosine 3x times 3, don't forget chain rule, dx. Since our substitution is sine 3x, we have to also account for cosine 3x dx. Dividing both sides by 3 actually solves and gives us cosine 3x dx. That can be traded out with a 1/3 du. Sine 3x is our u sub. Cosine 3x dx is 1/3 du. Taking the antiderivative, that's u squared over 2 times 1/3. That's 1/6 u squared. Remember that u is 3 sine of 3x. So that is 1/6 sine squared 3x. Now you can also put sine 3x in a big group of parentheses and put the square outside. That's totally fine. Plus c for your constant of integration. The next example, we have the integral of ex times ex plus 2 quantity to the 7th power dx. Ex plus 2 is found inside of a grouping symbol, so let's try that as our substitution. We'll let u be equal to ex plus 2. The derivative of both sides is du equals ex dx. We have our substitution to the 7th, u to the 7th. Ex dx is du. Antiderivative, u to the 8th over 8 plus c, replacing u with e to the x plus 2. So we have 1/8 e to the x plus 2, quantity 8th power, plus c. In our third example, we have the integral of e to the tangent 3x times secant squared of 3x dx. Let's let the power of e be our substitution. So we're going to set u equal to tangent of 3x. Taking the derivative of both sides and using chain rule, we'll have du equals secant squared of 3x times 3 dx. Let's go back to the original integral. We have e to the u, that's where our substitution. Secant squared 3x dx, if we divide both sides by 3, secant squared 3x dx is equal to 1/3 du. So we have an antiderivative of 1/3 e to the u plus our constant of integration, replacing u with tan 3x, gives us a 1/3 e to the tangent 3x plus c, and that's our indefinite integral. Switching to substitution method of definite integrals, we have the integral from 0 to 1 of x cubed times 2x to the 4th plus 1 quantity squared dx. 2x to the 4th plus 1, that's in a grouping symbol, so let's our substitution be equal to 2x to the 4th plus 1. Taking the derivative of both sides, that's du equals 8x cubed dx. We have our substitution squared. X cubed dx, once we divide by 8, we've isolated x cubed dx, and that can be replaced with 1/8 du. Now, when you substitute in a new variable, the lower and upper integral limits have to be filtered through that substitution. Our top integral limit of 1, when you put it, see, these two numbers are assigned to the variable x. When you trade out with a u, you have to filter those numbers through your substitution. So the new upper and lower limits, when we put 1 through, 2 times 1 to the 4th plus 1, that's over here in green, that's equal to 3. That's the new upper limit associated with the substitution variable of u. The lower limit 0, when we let x be 0, that's 2 times 0 to the 4th plus 1, and that's 1. That's our new lower limit. And I try to keep these things color-coded, so the green numbers are the new upper and lower limits that have been filtered through your substitution. Taking the antiderivative, that's u cubed over 3 times the 1/8 out front. That's 1 over 24 u cubed, evaluated at 3 and then at 1, and we'll take the difference. Now, since we're not going to switch back to the x variable, we leave the 3 and the 1 as our upper and lower limits. 1 over 24 times 3 cubed minus 1 cubed, and that's on this step. 1 over 24 times 3 cubed minus 1 cubed. That gives us 1 over 24 times 26. 26 over 24 reduces to 13/12. The next definite integral using substitution method we looked at was the integral from 1 to 9 of 1 over square root 2x plus 7 dx. Since 2x plus 7 is grouped under the radical, let's try it as our substitution. If we let u be 2x plus 7, then taking the derivative, we get du equals 2 dx. In the original problem, the only number we have to worry about is this 1. Well, there's an unwritten 1 here, so think of it as 1 dx, 1 dx. The middle of the integral, we have 1 over square root of u. That was our substitution. And then dx will trade out for a 1/2 du. 1 over square root of u can be written as u to the negative half. Now, I purposefully left off the upper and lower limits here. I did put them back in towards the remainder of the problem, and that's just so that we could absorb translating 1 over square root of u. That's u to the negative half. Now, as a reminder, when you switch from the variable x to the substitution variable u, these upper and lower integral limits have to be filtered through your substitution. So the top number 9, 2 times 9 plus 7, that's 25. Our lower number 1, 2 times 1 plus 7, that's 9. So 25 and 9 are your new upper and lower integral limits. Excuse me. Taking the antiderivative, we have this half that stays the same. All right, so for the antiderivative, we add 1, that makes it u to the half, divided by the result of 1/2. 2 times the half is 1, so basically this turns back into square root of u. Evaluated at 25, and then at 9, square root of 25 minus square root of 9, 5 minus 3, that's 2. I hope this helps out. Reach out if you need any help, and I'll do my best to help you out.